I recently had the opportunity to present on astrophotography, only my favorite topic in the entire universe, to the Twin City Amateur Astronomers Club here in Bloomington, Illinois, and it was a really nice time. We had some decent attendance. It was a very cold night, and people made it out still. We had a Zoom meeting with more attendees there, and so it was a lot of fun. I spoke for about an hour about getting started in astrophotography. I talked about equipment. I talked about capturing images. I talked about processing images, and then key considerations for getting into the hobby. So this is targeted towards people who are interested in getting into the hobby or have just gotten started in the hobby. So if you're a more advanced astrophotographer, maybe this video isn't really for you, but I welcome you to continue watching, and I hope you enjoy it. My name is Doug, and this is Astro AF.
Well, appreciate you. Appreciate your phone. Oh, you guys don't get along now or something? We are recording, so I've got to be careful what I say. Well, I appreciate you guys coming out on a cold night tonight. It's not as cold as it was last night, but it's still cold.
It's cold.
It's cold. So does that? We'll have to see if that affects your photography work when it gets this cold.
Yeah, I'll talk about it a little bit.
When it's just even going outside and turning stuff on.
Yeah.
Well, this is Doug, and he's going to be talking to us about astrophotography. And by the time he's done, you all will be so excited about it that you're going to go out and buy $10,000 worth of equipment and go camp out at Doug's house to learn how to do that. Right?
Yeah.
Should we turn the lights on?
Yeah, let's try turning the lights off. And I think I've got my ISO set okay where I will be able to see. Yeah, that's going to work out. Yeah.
You folks online, it's dark in here, but you can still, we'll do the best we can with what we have here.
All right. And thanks for helping out with the Zoom meeting, Dave. All right, yeah, so I'm Doug Reynolds, and this is great. Thank you so much for coming out tonight. I wanted to just do an introduction to astrophotography. We're not going to deep dive whatsoever. I'm just going to kind of cover what I think are the high-level elements of astrophotography. I'm an amateur astrophotographer. I shoot out of my backyard here in Bloomington, Illinois. And where I'm at is a light scale that's called Bortle 6, and that's a measurement of sky brightness, okay? Which is pretty decent. If you go out to Waynesville Observatory, that's a Bortle 4, so it's a little bit darker. If you were to go to Chicago, that would be a Bortle 9. That's as bright as it gets, okay? And there are people that shoot in city light pollution, and it can be done. Pretty fortunate, you know, Bortle 6 is definitely doable in the location that I shoot from. I don't have any lights from neighbors or anything like that. I back up to kind of a wooded area and a creek, and then the nearest neighbors are pretty far away. And so lighting from other backyards and things like that is really low for where I'm at. So I'm lucky for that. The overview on this, so I want to show you a quick video here in a moment. And it's my astrophotography from 2024. And I thought I'd talk a little bit through the different images. It's about 5 minutes long, but I wanted to talk about the images themselves and my gear and that I used to take those images and where I was when I took the images and things like that to give you an idea. And a little bit about the cameras. And I think I'm going to jump out of the presentation at some point when I deem fit. And I want to talk about cameras a little bit. And I want to talk about sensors and different sensor sizes, and then what those look like, at least with my telescope. I did an example on the Andromeda galaxy, so we'll take a look at that and what that looks like, because Andromeda is huge. Having focal lengths and sensor sizes matters for how you can frame a target up, and I'll show you the limitations that I actually have to work with on an object of that size. So we'll go over that and equipment and capturing images, processing images, and then just a few considerations about that. Equipment capturing and processing are the three kind of keystone points that I wanted to touch on tonight. So this is in chronological order starting from last January, and I love that that nebula. Here, the Great Orion Nebula. So these are taken with a camera that's a 1 inch by 1 inch sensor. It's an astrophotography camera. And this was with a 70 millimeter refractor telescope that is about 420 millimeters in focal length. So that's a little oblong on the screen, but yeah, so I did a little bit of solar. I don't really have a good solar setup, but I like to play around. And Pons Brooks, I was really fortunate to be able to catch that. And in fact, I went out to Waynesville. I had technical difficulties. I got one shot. That image was just one frame. Then the eclipse, I traveled over to Indiana and got into the line of totality there and was able to have a lot of fun photographing the eclipse. So we're still on the IMX 533 camera here with the 420 millimeter telescope. And then we had this amazing Aurora Borealis. It was the first one of my life that I'd ever seen. And it was here in Bloomington. That's okay, Whirlpool Galaxy. I had over 100 hours of imaging in this capture here. It went on for a month. And the Needle Galaxy, another one I had a lot. I think I maybe had 40 or 45 hours of imaging in this one. I don't recall exactly. And the meteor shower, this is actually with my iPhone, with a little app that does meteor shower settings for time lapse. This is an emission nebula. A lot of hydrogen alpha is the red here. I was messing around with the moon. We had the supermoon earlier this year. So now I'm actually on a different telescope. I'm on a Celestron EdgeHD 8, which is a Schmidt-Cassegrain telescope. And the Pillars of Creation, messing around with planetary. I'm not that good at it. I'm working on it. And I don't have a whole lot of equipment for planetary yet, and Saturn. So yeah, there's work that, for improvement to be done on these, but I was real happy. This was my first effort with an SCT of trying to capture planets. This was taken with the 533 on my Schmidt-Cassegrain and was a 9-panel mosaic. I'll talk a little bit more about that I did in one night. And then our supermoon. And this is also, I'm using something here on the Schmidt-Cassegrain that's called a hyperstar. And with the hyperstar, the camera is no longer on the back of the telescope. You remove the secondary mirror and the camera takes place in the secondary mirror. And so this is running at about 375 millimeters of focal length at this. And it's at f1.9, so it gets very, very fast. So these are all one night compositions here, like 8 hours max in this. Okay, so here I traveled out to New Mexico. I was at 7,000 feet in elevation camping and in Bortle 1, some of the darkest skies. Bortle 1 is as dark as it gets. There's no light pollution, no city lights, nothing around. This was with my iPhone in the Bortle 1. I was able to get the C2023A3 while I was there. I didn't have a whole lot of time in there. There's maybe 50 images, 30 seconds on that. This is the IFN, which surrounds Polaris. You probably wouldn't know it was there. It's full of dust all the way around Polaris, and you can't see it in higher light pollution areas. The Embryo Nebula, this is a dark nebula with hydrogen emissions, which are red. This is a dark nebula fail that I tried to do here from Bloomington, and it should be in the middle here, but I thought it was pretty, so I decided to keep it. Globular cluster. I like shooting those, they're fun. The lobster claw. So any of the square images, they're going to be with my 533. This one here this is a rectangular one, dark nebula. I took this from Bloomington. So this is what I do. This is my passion. This is I have a lot of fun doing it, and I have a lot of frustration doing it. Last night I was set up and ready to go, and it was clear into the evening, and then the clouds rolling. And I swear it teases me. You know, it's going, yeah, go ahead and set up, Doug. You know, and I'll run out there. So my telescope, I leave it set up year round, and I have concrete blocks on the ground that my tripod sits on. And then my tripod has 75 pounds of sandbag ballast attached to the legs that hold it down. And then I also have 3 really heavy-duty guy lines running down to stakes in the ground that tie on to the spreader plate on the tripod. And I've got that stake down and pulled down. And that makes a real stable, wind-resistant platform to put my telescope on. The reason that I did that is because the year before, I didn't have that, and the cables that I have running out, I have a power cable and an an Ethernet cable running out, and the dogs ran through the cables, caught it, and brought the whole telescope rig over. And so I learned about how to take telescopes apart and put them back together, and it worked out really well. And I was able to fix my refractor. It wasn't damaged badly. It had a Raspberry Pi on top that I was using for a controller, and it exploded and went like 30 feet, a lot of different parts. It was kind of impressive. And they were fine, you know, and I was, what do you do? So, and the entire rig fell over, and I have what's called an autofocuser. And the autofocuser sticks out from the side, and it's a little motor, it's a little step motor, and it actually turns the focuser for me. So like you'd take your hand on your focuser and focus your telescope. The autofocuser is a little motor that does that for you, and you can get very, very, very fine movements. In fact, it is like sub-nanometer increments, so finer than human hair, it will move the focuser knob for me, because focus is really important, and we'll talk about that in a little bit. The entire rig fell over, and it landed on the focuser, and nothing else hit the ground. So the focuser took one for the team, and that's the only thing I had to replace. I didn't have any dents or anything like that. I had the broken computer, ended up having to replace that, and I was back up and running in about a month. It could have been a lot worse. So
was that the refractor or the SCT?
that was the refractor, and that was kind of the impetus for thinking, I think I want to get another telescope. So, but nothing wrong with it. I still have a telescope, and I love it. And I highly recommend a telescope like that. A small refractor is so much fun. It's easy, it's light, and and portable. You can have a small mobile rig and go. But all right. So let's move on. I like to talk a lot. You can ask my wife. All right. So equipment: telescopes, mounts, cameras, guiding, and filters. Then we'll just do those in that order. And I'm going to speak from my own experience. I don't have experience with every telescope or types of telescopes and things like that. So my experience is with refractors and Schmidt-Cassegrains. So that's kind of where I'm at with it. But we'll hit on this and describe a few things. So refractors, they use lenses and or combinations of lenses. There's different types, the apochromatic and things like that, and those are different combinations of lenses that are designed to focus the different channels of light, the different colors of light, into a single point as much as possible. Okay, and that's the goal. And the higher quality optics, the better they do at focusing the different channels of light into that point. And where that point is hopefully on the sensor of your camera. We want those channels of light to come in and be in focus when they come to your sensor, and that is called back focus. So that's the distance from like the back of your telescope to the camera. So from the focuser to the camera. So at that point, normally 55 millimeters. So that's a standard. And on the Schmidt-Cassegrain it's different. But I like refractors. The small refractor is not a planetary telescope, in my opinion. It doesn't have enough magnification. You could probably push it, and then trying to get the object in frame and keep it in frame. And if in visual, it's nearly impossible, especially if you're manually moving telescope on your mount, then the amount of shake and things like that you get from, even, trying to touch one of the fine adjustment knobs or something like that makes it not very fun when you're that magnified. I much prefer to be backed out into a wider field, and I enjoy that more. The visual aspect of that is better. Now, on the camera, with a guiding telescope and precision, it's a little different because I'm not touching it. I'm not breathing on it. And I have really high precision instruments that are controlling where the telescope is pointing and where it's tracking. And that is a big difference, and it's a requirement for taking long exposures. Not so much for short exposures, maybe up to 30 seconds or so. Lately, I've been taking 10-minute exposures. So, and what that means is I have to be perfectly aligned on my target without any deviation. And for me, there's deviation, but it's about 0.58 arc seconds is the deviation in my guiding on my telescope. And that is well below, you could probably be somewhere up around 2 arc seconds and still get stars that are looking like they're in focus, that they're not shaking around, and your object is still retaining focus and things like that. So those are things that are important. So reflectors use mirrors, and they gather light, onto a primary mirror and bring that up to a secondary, which then directs it into your eyepiece. Or in this case, you'd replace your eyepiece with a camera assembly. So they work a little bit differently. And then the catadioptric, which is the kind of telescope that I have with the Schmidt-Cassegrain, uses a combination of mirrors and lenses. So mounts, arguably more important than the telescope in astrophotography, okay? I did not take that advice. I bought my refractor and I put it on a camera tripod, that one back there, in fact, and it was a horrible experience, but I got some decent photographs of the moon, and that was about all I could do, with it at that point in time. That was just me getting started, and I was like, I'm getting a telescope, but I should get them out. But the mounts are so expensive. I'm getting a telescope because I can get one cheaper, and I can get started, But it wasn't that enjoyable. So in order for astrophotography, the mount is probably the most important instrument of your collection. Secondary to the telescope, and then the camera. Obviously, there's lots of other things, but a couple different types of mounts are equatorial, which are like the German equatorial mounts, and they take into consideration through adjustment the angle of the Earth's axis and rotation, and they track across the sky in sidereal rate so that they can maintain an accuracy on whatever you're pointing at against the Earth's rotation. Alt-azimuth mounts need special computerized motors and things like that, or software to compensate for in astrophotography, because what happens is you end up coming around in an arc, and so your images will all be at different angles. Now, you can, in post-processing, get those all aligned, but then you have some heavy cropping, so you'll lose a lot around the edges because of, one image doesn't have a corner here, but another image is this way and has a corner here. So it can be done, but it might have some more challenges involved. But there's software for post-processing that can help you with that. So I don't have a ton of experience with DSLRs, mirrorless cameras. In fact, I should have Sandula come up because he does. From the beginning, I decided just to go with dedicated astrophotography camera. But that's not to say anything good or bad about either one of them. There are some benefits, in my opinion, to dedicated astrophotography cameras, which I'll get into in a minute. But the DSLRs are great. And I think the only one drawback on DSLRs, the commercial, is that every one of them is going to have like a UV IR, ultraviolet infrared cut filter built into it. And that is going to cause the loss of some of the frequencies of light making it to the sensor that we're really interested in, hydrogen alpha being one of the most prevalent light frequencies, in our universe that we know of. being one of them. So a lot of people will, well, you can get a commercial Astro modified DSLR camera, and that has that UV-IR filter removed. And there's also ways to DIY it yourself, which looks horrible. I've actually, and it's like surgery and it's messy. And I personally wouldn't take it on, but some people do it and it looks like they're destroying their camera, but when they're done, it works. So yeah, there's people that you can send your camera to get it Astro modified. I have no idea what the cost is. I think it's probably $200, $250, somewhere in that neighborhood. Don't quote me. Yeah, so anyway, that's kind of the consideration with DSLRs. You can slap a DSLR onto a T-ring adapter on the back of your scope, get the right back focus, which again is probably going to be 55 millimeters, and start shooting. So you can certainly do that. So dedicated astrophotography cameras, they're kind of the same. DSLRs, mostly the same sensors, different sensor sizes, the same things are available between both. Now, in my opinion, the biggest advantage of a dedicated astrophotography camera is, especially the ones that I use, they are cooled. And that means they have a refrigeration system on the sensor. And in this weather, it doesn't matter too much. Okay, but keeping the sensor cold in 40 degrees or above or something like that, I can lower the temperature of my sensor by 30 degrees from ambient down to like 30 degrees. Okay, so when it gets to 40 or whatever, I can start doing it. I try to go to -10 below ambient temperature, and what that does is it reduces electronic noise and hot pixels and things like that that'll show up in your images that then need to be addressed in post-processing. So if you can avoid having them in your image in the first place, then why not? And so having the cooler on the camera is one of the main things. There's color cameras. They're called one-shot color, OSC, and then mono cameras. My 533, which was the square frame, is an OSC camera, and those are great. You can put them on and start shooting. If you're in really dark skies, no filters needed. You can certainly throw, if you want to go for specific light frequencies, and we'll talk about filters later, then you can use different types of filters. Like normally with OSC, it's combination filters, and it would be like hydrogen alpha and oxygen 3 filters that can help you capture just specific bandwidths of light that are coming in. Mono cameras, my other camera, which is IMX4, I'm forgetting, 62, 63, something like that. I'll show it in a minute. Is just that. It's mono. It doesn't have any type of Bayer pattern or anything like that, and I'll talk about here, which is a pattern of light color channel sensitive pixels that on a color camera sensor. On a mono camera, it does not have any Bayer pattern on it at all. The sensor is mono, and then the reason that we use filters with a mono camera, we use RGB filters. That way we can capture the RGB channels independently onto that. So the entire sensor is capturing red when you have the red filter in. The entire sensor is capturing blue when you have the blue filter in, etc. And that gives a little bit more detail, more signal, in my opinion. I'm sure that can start an argument on this. It just makes sense because on a normal Bayer pattern, which is going to be like LRGB, so for every red and blue pixel on your camera, there's going to be 2 green, and that's because of the way that humans see things. And so they designed this Bayer pattern. So the camera sensor on an OSC is dividing the light that you're getting for each exposure across different pixels on the camera sensor for different colors. So you're getting twice as many green pixels that are capturing light as you are the red and the blue. So when we actually process the images in OSC and you bring them all together, it'll come up and it'll be bright green. When you first get started, you're like, what went wrong, you know? And it's just natural. It's exactly the way that it should be. And then we go through a processing to level out all the colors. And if you look at those colors on a histogram, the green will be way up on the histogram, and the red and blue will be way low on this histogram, and we need to level those out. So we just go through a process to calibrate those colors.
Hey, Doug,
Yeah.
couldn't you just have RGB and then boost the green in the post-processing?
You could if you want, yeah. But on an OSC, you wouldn't want to, because you've already got double the green. But on a mono, yeah. And on mono, you can do whatever you want. You know, on mono, I could do like a sulfur, hydrogen, and oxygen, and then do a Hubble palette, and you'll see it look green, like what we saw in the Hubble images. You know, so the hydrogen alpha, they're running through the green channel, and since hydrogen alpha is the most prevalent light frequency that we have coming in, you know, on these targets, then we get a substantial amount of green in the image for that reason. So yeah, there's all kinds of different palettes and different combinations that you can run these color channels through to get different false colors, or you can keep them lined up. And I tend to gravitate towards real colors when I can. Like the Orion Nebula image, that was hydrogen and oxygen data only. And it was HOO, so H took the red channel, oxygen took the green channel, and oxygen also took the blue channel. I think there was some blending in the green channel of hydrogen in there as well, but that's how I got to that. So that was a HOO, which is a color palette.
How does it compare with the one-shot color for the same image? You know, what kind of palette do you go with?
Well, if I go take an image with a one-shot color and I don't have any filters on it, then I get that image, and then I separate it into RGBs if I want. But I'll get that image as an RGB. I don't have to separate it. But if I want to work on the individual color channels independent of the other ones, I can in post-processing, and I can split channels. You can do that in Photoshop or any imaging application that you may wish to. But
I'm lazy enough to always use that option.
yeah. No, you can split channels, and you have all the flexibility to work with it any way that you want. All right, guiding. So guiding is really important. So this is where it allows you to start getting into the longer exposures. And the reason that we want longer exposures is because when we're photographing dark things in the dark, there's a lot of noise, okay? And what we're interested in is in the signal. And what we need to have happen is to get enough signal to swamp out the noise that gives us a good signal to noise ratio. It is arguably, who knows what a good signal to noise ratio is? It's what your eye sees on your images. And as you're capturing data, maybe it's multi-nights. For me, it usually is multi-nights, and I start adding data in. I look at it, and I do like a fake processing in the mornings just to see where I'm at and if I think I'm done or not. And generally speaking, here in Bortle 6, I'm going to have 20 to 24 hours of imaging time, so I'll have 3 nights, 4 nights, depending on weather or whatever. But guiding allows me to take the longer exposures and get more light signal into those exposures to swamp out the noise from the rest of the dark that's there. So what happens is I have a piece of software I use PhD2, and PhD2 uses a guide camera. It's a second camera that's on my telescope, and it's looking at stars that are around my target. And it's going to pick a star and put a reticle on it, and it's going to measure it repeatedly. I take an exposure every 3 seconds to measure the star, and whatever that star deviates, that software will send a pulse to my mount and tell it to move in a certain direction by a certain amount based on how long the pulse is. And so that is continually throughout the entire session correcting deviations of my mount's tracking. And so by minimizing tracking errors, basically I'm simply stationary on an object which in our perspective is moving across the sky. And that's what you need in order to do long exposure. So like I said earlier, you could take maybe up to you'll start seeing star trails at about 30 seconds if you went out with your iPhone tonight, and they would just start elongating at 30 seconds. You could take like a 10 or 15 second image, it'll look great. The stars will be pinpoint. So if you wanted to take a lot of 15-second images and stack them together, you could certainly do that and not need to have a German equatorial mount and guiding set up and things like that. Okay, so that would be a good way to get started. That's what I did with that little thing there. But then you're still running into the noise. So that means you're taking 1,000 15-second images or whatever, where in my 10-minute exposure nights, I'm going to have 10 or 15 of each channel, LRGB, for an entire night session. So, but in the end, the sum of all those images that come together is your total exposure time. So they are somewhat equivalent. The thing is that the longer exposures allow the well of the pixel to fill more with electrons over the long period of time, and that's more signal per image. So that arguably, I think, has some benefit. All right, filters. There's a lot of stuff about filters, okay? Light pollution filters in our area, really need one. UV IR cut filter for your camera, which is specific for astrophotography. And it's different than the type of filter that's built into the DSLRs. This one actually will have an open bandwidth of 400 to 700 nanometers of light spectrum to allow all that light to come in. But the filters will have specific frequency cuts built into them that are akin to the color of the street lights and other common frequencies of city lighting and things like that, and moonlight. It can help you with, if you've got a bright moon, that can affect your images too. So UV IR cut filter will help with that. Multi-bandpass filters, I mentioned before, like an hydrogen alpha oxygen 3 filter, then you can have multi-bandpass filters that cut everything out except the frequencies of light that you're interested in. So if you want to get hydrogen, you want to get oxygen, or you want to get sulfur, whatever, those all have different frequencies of light. And so you can apply those filters both to OSC and to mono to limit what frequencies of light are coming in and hitting your sensor. And then, you can create your composition from that.
So you have like a filter for HA and a separate one for the O3 and stack them together? Or you just get a single filter which has both band passes?
I have 7 filters, and I have an electronic filter wheel that rotates them automatically for me. And so I will actually set up a sequence that says take 3 hydrogen alpha images and then switch filters, and then take 3 oxygen 3 images and switch filters, and then take 3 sulfur images. And,
so these are specific filters for a specific frequency, and then, okay.
Yeah, and then those get combined together. When I process those, I'll end up with 3 images. And then I work with the hydrogen separately from the oxygen, separately from the sulfur, and then I combine those together to for the actual RGB composition, that's created from that. So the multi-band pass filters, which are kind of like what you just said, it wouldn't really stack them. They're one filter that actually is designed to block certain frequencies and allow other frequencies through. And so it would be one filter that has 2 band passes on it. That's called a dual narrowband filter. There's tri-band filters. I think I just saw a quad band. I don't even know how you process those things. I don't have one. But I would imagine you're going to get 4 images out of that if your processing software can do that for you. And then you can work with those channels from there. So LRGB filters, that's what I use with my mono camera. So luminance is the entire spectrum. Okay, and it is not a color channel. It is a lightness channel. So that is the detail and brightness of the image. RGB are exactly what you think they are. So red, green, and blue filters. And so when I do my sessions for color here, standard colors, then I'll do LRGB. So I'll have 4 filters that I use throughout, the entire night of sessions or multi-night sessions. And yeah, so the range of the luminance is 400 to 700, generally speaking. And then, so yeah, red is in the 600 to 700 nanometer range, and green is in the 500 to 600, and we're stepping down, and blue is in the 400 to 500 nanometer range. And so those are basically saying block everything else except what's in there. And the filters are also have specifications like maybe like a 12 nanometer bandpass. That means that, you know, if they're centered on blue at 450, then plus or minus 6 on either side of that, which it isn't actually that way. It shifts, and there's different quality control, depends on the filter. You can get cheap filters, you can get expensive filters, and quality tends to follow your money on that. Narrowband filters, so these are specific filters for specific bands of light. So as we were talking, the sulfur and hydrogen and oxygen, so which we pretty much went over that. You know, and those have their specific bandwidths here, 672 for sulfur and 656 for hydrogen alpha and 495-ish for O3. And again, the filter that you're using will have a specification. I use 7 nanometer band passes, so 3.5 to both sides approximately, because narrowband is what you want. As narrow as you can get. There's 3 nanometer band passes, you know, so they're getting very, very tight, very, very expensive filters. You know, if you really want to get rid of everything except that specific bandwidth or frequency of light, then that's the way that you do it. Capturing images. This is an image of my software that I use for my sessions for when I'm actually capturing. And this is a focus curve here. Each one of these dots is a point of focus. This is more out of focus, and this is more in focus down here. And so it goes through and changes the focuser and steps through, and through a hyperbolic curve here determines what the lowest point of focus is. And it does that through measuring what's called HFR, which is the half flux radius of stars. And that is the radius of light from their brightest point in the center. And the smaller that you can make that radius, the more in focus you are. And so this is what this is doing, is saying this is the smallest that it could get the stars it was measuring, and this is the largest that it took the stars. And it does this so that it can determine where that point is, which is basically down here below that. This is a guiding graph here. And what these lines are, this red line that's coming up here and these blue lines that are here, these are adjustments to my RA. And the length of these lines is the amount of adjustment that was needed. This was a big correction here. Something happened, maybe a gust of wind or something like that. I don't know. And then there's a lot of smaller corrections it's making just as things are moving around or whatever. You know, the image itself, this is an HFR graph here. My first image had a higher HFR than my second, so my focus actually improved. That could have been a cloud came through or something, I don't know. Could be anything, but I kind of like to keep an eye on that. I actually have my focuser autofocus if HFR deviates more than 10%. And then if it does that, then I know that I've gone out of focus. There's things that can, temperature changes throughout the night and things like that can change your optics and cause a need for focusing. Each one of the filters, they're as parfocal as you can get, but there's a difference in the focus between one filter and another. And so I calculate those on an initial setup, and then when I change filters, the focuser automatically compensates for the next filter that comes up and puts it in focus without having to go through. This takes about 3 or 4 minutes. So by doing the automatic focus, I can save that time. It just automatically switches because it's going to be pretty much that delta is going to be the same between filters all the time. So yeah, focusing is probably the most important thing you can do for visual or for astrophotography. So precisely adjusting your telescope to achieve sharp detailed images in this case, or sharp detailed view. If you're doing visual, the goal is the same, to get it as good as you can. The way that you get there for astrophotography may be different. Now, I can go out with a Batinov mask, which is a really cool device, simple, cheap, and it is a specific design of different angled lines and things like that diffract the light in such a way that when you put it over your objective lens, that when you take a picture of a star, or even you can look through your telescope and use one of these two to focus manually, and it will set out a series of diffraction spikes. And the goal on those is to actually get those, if you had like 6 spikes coming out, all intersecting in the middle is your goal, going out in different angles. Well, when it's out of focus, they won't intersect in the middle, and a line will come through the top, and so, and it'll be out. And so you'll adjust your focus until you can get those lines, to meet in the origin at the center of the star, and you're in focus. Use it all the time, especially when I've torn down, reset back up again. I use it for making sure that I'm collimated correctly on the SCT, or you might need that for a, any other type of Newtonian type of telescope. But so yeah, anyway, it's really important. For solar system objects, it's a little bit different. You generally will go and look at a star and get focused on a star to begin with, and then go over to the object or planet that we're, moon or whatever, and then we'll be looking at focusing on the edges of that target. And center mass, if you're using some tools like SharpCap, has some other ways to go about that, where it's actually calculating the mass of the object that you're at on center, and then figuring out the focus around the edges, based on center mass. And I talked about HFR here already. So framing's, I love framing. It's really a fun part, because it's where I go through the sky atlas and figure out what it is that I would like to shoot in my next project, which is at the beginning of every project, and when I'm like, okay, what's next, and go through and just what's in the sky tonight, and do that research and start looking at other people's images on AstroBin, and get an idea of how I'm feeling, what I'm feeling, if I come up with ideas for composition on something. But the framing is important, and so what we're looking at here is my camera sensor here, and the object. And I have the ability then through my software to bring up this image from the sky atlas and place my camera sensor rectangle on this, so that I can decide on how I want this framed. And then I can move this target, where I want in my frame, and I can rotate my frame. That would be rotating my camera, okay? And moving this target back and forth, that would be realigning my telescope one way or another, okay? And once I get decided on that, then I have a set of coordinates based on that that are in my system, and I can tell my telescope to go there. I can take an image and have it tell me what's my rotation, and so it'll come up and say, here's this, but this isn't what I'm actually seeing. So I take an image and tell me my rotation, and then it'll rotate this rectangle to where I'm actually at, so I can see how I'm framed up on the target before I start my imaging session. Stellarium is a great program. You might have used it. It does this type of thing for you, and you can control your mount with it. I use a piece of software called Nina. It's open source and free, and it is very powerful, and it does things like this for me. Once I get set on it, I can send this out to a sequence, and my target is set, and then I can just press a button that says, go to that target. Let's go to mount, and it'll go there and line up on it. I have a database of celestial objects that it'll go compare to make sure that I'm aligned. If I'm not, it'll give corrections to the mount to move it until what images I'm taking with my camera match the sky atlas. And once it's aligned and rotated as I've told it to be, then I can start imaging at that point. So short exposures, bright objects, if you don't want to swamp your pixels with light and fill up the well and it overflows and you just got electrons that you're not using, and you're basically getting clipping at that time. It's too much data, and you're overwhelming the sensors or overwhelming the pixels. Long exposures allow you to get at faint objects and get better signal to noise ratio, but you have to have the accurate tracking and guiding in order to do that. again, back on star exposures, as we said, you can prevent star trailing. It's a great way to just get into it without having to go through the expense of the mount and stuff. And to start there, I recommend that. That's a good place to start. You could do it with your iPhone, honestly. And there's some limitations on that because iPhone, you have to have a tripod to get a longer exposure, 30 seconds or whatever. It doesn't really give you the ability to do like a 25-second exposure or a 20. So it'll say, yeah, you can do a 10, or you might be able to do a 15 or a 30, but you're not going to get anything in between there. But I have fun with that sometimes, and with any of the wide field sky stuff like the Milky Way and meteor showers and things, and I like going out and just setting my iPhone up on a tripod with a time lapse and let it run. So multiple exposures. So we take many exposures to do what we do. And so that, like that long exposure, if you took, you could go out there and take a 15-minute exposure if you wanted, and that would be fine. People do it. You could also take 3 5-minute exposures and to get to the same signal and noise ratio as one theoretically longer exposure. So guiding, the auto guider, I talked about this, and so what I have is I have an OAG, which is on the bottom. So, but what you have is a guide scope, and that's going to be kind of like the scope, your alignment scope that you have on top of your regular telescope, and you're looking through it, and it's calibrated with your through that little scope is going to help you be aligned on your larger scope, right? So in this, where it's kind of the same thing, except we got a camera slapped to the back of that guide scope, and it's measuring the stars as I mentioned. Now in my case, I use an off-axis guider, which goes in line of my image train, and it's a prism, and it fits down in just outside of the field of view of my camera and the sensor. And light comes in and it directs it straight up through that prism into another camera here, and that camera sends image data to my software PhD2 that then calculates and does the guiding corrections for me. So either way, those are both really good ways to do guiding. I don't have a preference. I just off-axis guider reduces weight and allows me to be focusing my guide camera on the same beam of light that's coming into my telescope. So when I change the focus on my camera, the focus automatically changes for my guide camera as well. I don't have to focus them independently. So that's why I like off-axis guiders. Yeah.
Why couldn't the guiding come from the software itself, the imaging software?
Well, they use a separate camera for it. I don't know.
You would think, but
Yeah. I mean, they've even got cameras that are dual sensor in one camera. One's a guide camera and the other one's your main imaging sensor. So for some reason, and it might be because trying to process the image data and use it for guiding at the same time. Well, another reason is because the guiding camera is taking 3-second images over and over, and my main camera is taking 10-minute images. So it can't send. Yeah. So that's the reason. All right, so lights and calibration frames. So this is when we're done imaging. We need to do some calibration frames. And if you've been in photography, you know what these are. We've got light frames, which are the images that of the objects you're taking. So that's that's your M42 or whatever. That's your target. Dark frames are, well, as I say here, they account for sensor noise and thermal and electronic noise. You need to take these about every 6 months or so. You put the cap on, and this is at the same exposure time and temperature as you intend to take your light frames. This is where an astrophotography cooled camera comes in handy, because otherwise, if it's summertime, or whatever, you've got to take these dark frames for big temperature swings. So you might have to, and that's the same exposure time. So if you had an 8-hour session, you're going to have 8 hours of dark frames. And so people kind of end up not using calibration frames because it's really not realistic to do that. With the astrophotography camera, I'm able to, and I only need to do that. It's cloudy out. I think I'll make some new dark frames, and I have it covered up, and I just set it and let it run. In the morning, I've got all my dark frames. I create a library for them, and then throughout the year, So I basically do 30 seconds, 60 seconds, 2 minutes, 5 minutes, and whatever, and I just do the whole stack of different exposure times at negative 10 degrees Celsius, because that's what I always run it. And then I have my library. What you do is in processing, these dark frames are going to be there's a mathematical process that's going to be used to correct your light frame for any of these defects that come from noise or thermal or whatever. That'll be subtracted from your image. Bias frames subtract electronic readout noise and stuff like that are actually generated by the sensor. And this is with the lens cap on it, the same temperature, but I believe this is the shortest exposure time that your camera is capable of taking. And so these go really fast. So, you might be just some milliseconds of images for your bias frames. Biases will usually, I think, biases subtract from flats. And I think flats, there's a division in there. I don't actually know the formula for it. I don't have to worry about it, though. You don't have to worry about it. The software does the math for you. So flat frames, I do this every morning. And I point up at the sky in the zenith. And I set my exposure time on these based on the ADU, which is the brightness level on a histogram of about 40% of my camera's maximum brightness. And whatever that exposure time is. So if the sun's just coming up and it's it's not very bright out, that might be a 7-second exposure. If the sun's already breaking the horizon, that might drop down to a 1 or 0.5 second exposure, whatever that may be. We're going by the ADU on the histogram. So those dark frames, those correct stuff like dust motes on your optics. And you can also do dark frames. If it's cloudy out, you don't want to do dark frames on clouds. Or flat frames, I'm sorry. You don't want to do flat frames on clouds. So I've got a LED light panel that, like a tracing panel for an artist. I'll set on top of my dew shield and turn that on and then just run my flat frames on that. But you can do sky flats. That's the most convenient. You don't have to run out there and do anything. You just point your telescope at the zenith in the morning, and if it's a clear sky, you can take perfect flat frames. Dark flat frames are an option. I don't use them, but it's a combination of taking the same settings as your flat frames. So they're basically dark flats. So the only difference is the settings for the dark flats.
Just for reference, it's a little bit after.
Okay, we're almost there. Thank you. So processing, I'm going to move through this, okay? So we have stacking and registration and stuff like that. I know I have a lot of slides here. Oh, we're getting short, so.
We're okay.
Yeah, I've got a hard stop here pretty soon. I've got to go. But so this is the goal. We got our data from our capturing process, and we want to process it. We're going to stack the images. We're going to take all these multiple images that we took, and the software is going to take all these 5-minute images or whatever the exposure time that we took. It's going to stack them together. Okay, it's going to create one image out of many. And we've talked about why. Registration is going to happen during this process, and it's going to align all of the individual images by the stars through a star database and ensure that when we stack these images together, they are aligned. Calibration, so we're going to apply those calibration frames that we took, our darks and our biases and such and flats, to remove noise and correct. You could have a big dust mote on your lens, and these will take it out. If there is a dust mote and you can see it on your flats, it will be subtracted from your image and make the correction for you. Cropping, so when we stack all these together, we get some artifacts around the edges because they're not perfect, okay, as we're moving across the sky. That little bit of deviation that I talked about, that might be 2 arc seconds or less, you'll see that around the edges of your image after they're registered and stacked. And so we do cropping to cut that out. Background extraction, we're going to neutralize the gradients in the background with this. That could be moonlight coming in from one side, and you'll be bright to dark. And we can correct that through background extraction and neutralization. Color calibration, this is, so remember when I said on the Bayer pattern RGB and we had green, it was way up here on the histogram, and red and blue down here. We're going to calibrate that color to get those levels correct. And we can also use a database of color calibration on stars so that we can get accurate color calibration from the database. Stretching, that's when we get these, they're in what's called a linear state, and a linear image, you will just see black with a couple of little white dots. Okay, that image is linear, and all the data is in there, but we can't see it. It's basically the way that we would see it if we went outside and looked at it, you know. And but then we go through stretching and we pull those levels up of that data. And this is where the signal to noise ratio really matters, because as we pull those levels up, we're going to be bringing up that noise with it. And so if we have more signal than noise and our ratio is good, then that signal will swamp out the noise that we have in the image. Curves adjustments, this is kind of like stretching, except we're dealing with color channels and lightness channels. We're also dealing with chrominance and saturation and some things like that. So it's really just refining those levels of those different types of things. So the RGB channels and luminance channels and things like that. Sharpening, so we're basically working on enhancing the details. We're trying to, and noise reduction, these two things go together. And this is processing to reduce noise, but to still make things sharper. There's lots of techniques around it. This can be very frustrating. And sometimes you realize I need more data. And so you got to go out and do another night and bring more data in so you can get rid of noise, you know. So this is kind of what tells you if you've captured enough data or not, because if the noise is overwhelming in your image and you're not happy with it, that's just because you need to take more pictures. So key considerations: expense. It's not inexpensive, and it can be as expensive as you want. All right. If anybody here owns a boat, you don't have the right to say anything. Okay. So if you golf, you understand, all right? Because you've got your annual greens fees, you've got your golf equipment, you've got your carts, you got whatever, your shoes and everything else. It is very comparable to being a very serious golfer, I think, you know? And so something along those lines. If you're a bicyclist, you know, and all the gear and bike and everything that goes along with that. So this is another hobby. All right. And if it's your passion, then investing in it is investing in what you love, you know. So that's kind of what it's about. Light pollution, if possible, get out of the light pollution, go to the dark skies. I like to do that once a year anyway, because it's just amazing. And to be able to see the skies without the light pollution, the way that we used to be able to see that, it just gets me every time. And also elevation. The higher you get, the less atmosphere you have between you and your target, and that helps with getting better, more detailed images. Clear skies, we need them. You know, we are limited to what we can do based on our weather conditions. So minimal wind and clear skies and good seeing. And patience, because we got to wait for clear skies and no wind and seeing. Okay, and it just takes perseverance. And some nights it's like, great, you know, we're on. And other nights it's, you know, what do you want to do? So yeah, thank you. So thanks for watching this video. I really appreciated the opportunity to present to the Twin City Amateur Astronomers Club, and they're a great bunch of people with some really excellent resources for our community, and it's really a privilege to be able to spend time with the group and to get in front and talk about astrophotography, which is my passion. So anyway, I want to thank you for being a subscriber, and if you're not already subscribed, please take a chance to go hit that button below and give a like if you like this video. So anyway, thank you very much. And my name is Doug, and this is Astro AF.